finding some of these problems that I had assigned were not in the key because I assigned those problems last year and nobody complained about them not being in the key last year. So what was the deal? So I went onto Moodle and downloaded the notebook and saw that they were not there. But then I went to last year's and downloaded that, and it was there. Those exercise solutions were there. I don't understand because I thought I copied last year's Moodle into this year's Moodle, so those should have all transferred over. Anyway, long story short is I re-uploaded an updated Chapter 5 solution key that's got all of the missing problems in it, which actually also included a bunch of problems from the next section, section 5.4. I will still have to check chapters 6, 7, and 8 to make sure all the answers are there for those too. And we don't have a similar kind of problem. But I think I will go over some of those problems anyway, to some degree. That's part of our lecture today. Before we do that, let's just review what we've learned in chapter 5 overall, except for the very beginning, except for the definition of Riemann integrability. Let's review the theorems, some of which are not on the Mathematica here. I'll just label this properties of integrals. And the going assumption in every single one of these properties is that all functions that I write down will be Riemann integrable over the given intervals. Assume as a background assumption that all functions that I mention are Riemann integrable over the relevant intervals, unless said otherwise. So I'm not really going to state these properties as theorems. I'm not going to state them as equations and inequalities. One property is linearity. Well, you could write that as a bunch of sub-properties. You could say the integral of a constant times a function is a constant, that constant times the integral. Careful with our notation here. F is a function, C is a constant. C is any constant. You can pull the constant out in front. That's a linearity property. You can also say that the integral of the sum of two functions is the sum of the corresponding integrals over the same interval. You could combine these. You could write a linear combination of f and g. In fact, you can write a linear combination of any finite group of functions. And in fact, property C that I'm about to write down for the integral of a finite linear combination of functions really includes properties A and B. Right? I could just write down property C here. I'm writing it separate, but it really includes properties A and B. Okay, that really includes A and B, right? Property B would follow from this with n equal to 2 and C1 and C2 both equal to 1. Property A would follow if all the C's except for the first one were 0. So we only had one function. Pull the constant out. That property really includes A and B. By the way, you should not shy away from writing that in summation notation. It says the sum k goes from 1 to n. Well, okay. Other way around. This says the integral of a sum, which I'll put in parentheses here, though it's not traditional to put parentheses. is the corresponding sum of the integrals of the constant times the integrals. In effect, it's kind of like you can distribute the summation sign through the parentheses here. Well, the c's can be distributed into the integral effectively, and the summation sign, in a sense, can be distributed into the integral. It's kind of a way to imagine that. Okay, don't take that too far. Just notice how that way of writing it is equivalent to this way. So you should be comfortable seeing it like that. What other properties? We had if f of x is always less than or equal to g of x for all x in some interval, and again, assuming f and g are Riemann integrable, then the integral of f is less than or equal to the integral of g. And in particular, that also means, maybe I should list that as two sub-properties here. That also means if g of x were a constant function, call it m, the output was always m, then the integral of f would be less than or equal to capital M times b minus a, which is the same as the integral of the constant function m over the interval from a to b, the area of the rectangle. That's the geometric interpretation, at least when the graph of f is above the axis, the area under the graph of f is less than or equal to that area, and m is positive. But actually, this stuff works even if f goes below the axis, and even if m were negative, this still works. And some inequality still works that same direction. But the area interpretation is not the same. What other properties going on? Well, the next section was more big theorems, which I'm not going to write on the board. I've got in Mathematica here. Section 5.2 were those theorems whose proofs were pretty tough. Unbounded functions are not Riemann integrable. The book states that as if f is Riemann integrable, then it's bounded on the interval. Contrapositive of that then would say if you've got an unbounded function, like it's got a vertical asymptote on the given closed interval, then it would not be Riemann integrable. That's the contrapositive of the book statement. And contrapositives mean the same thing. They are equivalent. Though, once more, I will remind you that that fact is not contradicted by the existence of some improper integrals where your function's got a vertical asymptote. Because we're not talking about improper integrals here. There's that equivalent condition for Riemann integrability in terms of the oscillation. I'll just say that. You can look it up if you want to remember what it looks like. More importantly, ultimately for us, we want to know that continuous functions are Riemann integrable. Monotone functions are Riemann integrable. There are certainly plenty of functions that are neither continuous nor monotone that are not Riemann integrable, but these conditions are sufficient. If you know your function's continuous or you know it's monotone, even if it's not continuous, then your function can be integrated. It's Riemann integral. The idea of the area under the graph makes sense according to Riemann. What other properties of integrals? Some that I haven't mentioned beyond passing here, I'll talk about a little bit more here today. What I'm about to write down is actually more of a definition. You can call it a property, but it's not something you prove. It's a definition. If A happens to be bigger than B, there's going to be two definitions here as well. then the integral from a to b, well, it's this lower limit is bigger than the upper limit. By definition, this is the opposite of the integral from b to a. It's a definition there. It's not something we prove. We define that to be the case. We also, by definition, say that the integral from a constant to itself of any function is 0. And actually, I guess you could say that's any function defined on this degenerate interval that's just 1 point, because any function is going to be continuous on a domain that consists of 1 point. So the Riemann integral, the degenerate case. These are definitions, really. Do they make good sense? I claim they do. We could probably try to motivate them with physics, actually, a motion kind of situation. Say that the function you're integrating is your velocity. This is just a side note here, you don't have to write this down. Let me even emphasize that it's a velocity by writing v of t. So that's a velocity in meters per second, say. What's the integral of the velocity represent in physics? Well, that's the integral of the speed as distance traveled, but when velocity is allowed to be negative, its displacement, change in position, is what that equals. Displacement change in position, which can be positive or negative. Let's say position 0 is right at the edge of this table here. Positive positions are to the right and negative positions are to the left. If I move back and forth, if I move this way with a positive velocity, then turn around and move back this way, I have a negative velocity. Maybe I stop right here. The integral of my velocity is my change in position. It's this positive quantity. I went from here to here over that amount of time. I could have kept going past the initial position of 0 into negative positions on a number line. Then my change in position would have been negative. This can be interpreted that way, whether A is less than B or vice versa. Typically, we think of A as being less than B, and so I'm moving as time goes by and I change my position. Maybe my change in position is negative here. But what if I switched it around? The integral should be the opposite of the original integral. What does that correspond to? It corresponds to physically moving backwards in time, right? It's like if we videotape myself, like we're doing right now, and watched it in reverse, my change in position would then be positive, going from there to there as time goes backwards. Does that make sense? My original motion forward time ended up in a negative change in position, but then if I run time backwards, then I go from there to there, and that's a positive change in position, the opposite of the negative change in position. And that one can be justified as saying, if no time elapses, then there's no motion. So this is listed under properties, but this is really a definition. The following equation that comes from breaking up an interval into two pieces is true. Certainly it can be proved, or should be proved, as a theorem when C is between A and B. And in fact, the book does prove it as a theorem in that case. However, once you've got these definitions here, This is true actually even if C is not between A and B. Though it's harder to understand the meaning. So this fact is true actually no matter what A, B, and C are. C doesn't have to be between A and B. Believe that? Should we sort of think about one case? Think about it over here. Let's pretend C is over here. Well, I want to verify this equation works. Even when C is over there. C is not between A and B. However, in this picture, A is between C and B. So I could certainly write down that the integral from C to B would equal the integral from C to A plus the integral from A to B. Which makes sense if you think about areas. Imagine the graph is above the axis. You can make sense of this kind of thing by thinking about areas. The total area is the sum of the two smaller areas. That doesn't quite look like this. Can I make it look like that? It's not clear that you definitely can. Let's see, if you solve this equation for the integral of f from a to b by subtracting this integral from both sides. Oops, get the direction right. Had it right before. Subtract that integral from both sides. Cancels on the right side. On the left side, you get this minus this equals the integral. I'm going to switch around the order. The integral of f from a to b is the integral of f from c to b minus the integral of f from c to a. Doesn't look like this yet until you use this fact. The negative of the integral from c to a is the same as plus the integral from a to c. That now matches this. Okay? So this has to be proved using the definition of Riemann integrability, or in fact the equivalent form, in the case where C is between A and B. But once you've got this definition, and this one as well, C could equal A or B, then this property can be seen to hold no matter what. Okay, so these are fundamental properties of integrals that you should know. Then there's the fundamental theorem of calculus. I didn't mean to use the word fundamental twice, but they are fundamental. They are all of basic importance. Let me state the fundamental theorem of calculus the way the book does, and this time I will state it in a stronger form that the book states it in. Suppose you've got a function little f that's Riemann integrable on some closed interval, and, well, okay, in part 1, part A, we define this new function, capital F, by integrating little f over intervals of this form from a to x to find our different values of capital F of x. Technically, you need something that I didn't mention. If a function is Riemann integrable on some interval, some closed interval, it's also Riemann integrable on any closed subinterval of that. The interval from a to x is a subinterval of the interval from a to b. I am assuming x is less than or equal to b here. You can say for sure that capital F is continuous. That's one thing you can say. For sure, as long as little f is Riemann integrable, little f could be discontinuous. Moreover, and more importantly, if little f is continuous at a number, I think the book goes ahead and calls it x. I'll call it something else. I'll call it c. At some point c in the interval, then capital F is differentiable at c, and capital F prime of c equals little f of c. So I think the book uses an x again, but I'm using a different letter here since my x I used there is my variable for capital F. But you can, variables, they can always be thought of as being constants if you want them to be. If you want to say, I'm imagining this to be a fixed number, you can go ahead and do that.
Is when it says if f is continuous at c as long as it is that f big F or little f?
This is little f. If little f happens to be continuous over the entire interval, then capital F would be differentiable over that entire interval and would be an antiderivative of little f over that entire interval. That's why this is sometimes called the antiderivative construction form of the fundamental theorem of calculus. You're constructing an antiderivative using an integral. Areas can be used to find antiderivatives, is the idea. Part B is the flip side of that. Antiderivatives can be used to find areas. If capital G is an antiderivative, of little f on the interval, then you can evaluate the integral of little f by doing capital G of b minus capital G of a. That's the one you're more used to. Part A says areas, or more precisely signed areas, where you count areas when the graph is below the axis as negative contributions to the integral. Areas can be used to define antiderivatives. Part B is really the flip side. Antiderivatives can be used to find signed areas. You can prove part B actually pretty easily from part A. That's actually number 14. Let's go ahead and do that. Proof of B from A. So we're going to assume we've got an antiderivative of the given function on the interval. So g prime of x equals f of x for all x in the interval. So a little bit of a fly in the ointment here. Doesn't necessarily mean f is continuous. antiderivatives do satisfy the intermediate value property we've seen, but are not necessarily continuous. Okay, in number 14, they go ahead and they add the extra assumption that little f is continuous. It can be proved without that assumption. Part B can be proved without the assumption that little f is continuous. And in fact, that's the point of problem 12. Essentially, I think. Let's see. 12 and 13 combined, actually. The point of 12 and 13 combined, I'm not going to talk about those problems, but you can look at them, is that you can prove part B of the fundamental theorem of calculus here without assuming little f is continuous. It's still true even if little f is not continuous, is the point. Because derivatives don't have to be continuous. G can be an antiderivative of little f without little f being continuous. So if we're going to use part A to prove that, I'm going to need the continuity of little f because the second part of part A assumes little f is continuous at the point. Or I should say on the entire interval. That's going to be my assumption. So I can use part A is the idea here. I'm trying to use part A to prove part B. But if I'm going to use part A, I'm going to need little f to be continuous. And that is what the book says to do in number 14, is assume little f is continuous. So what do? Okay, so I'm assuming capital G is an antiderivative of little f. I want to show that this equation right there is true. How do you use part A? Go ahead and define a capital F. And since little f is continuous, on the closed interval from A to B, capital F prime of x equals little f of x for all x in that closed interval. In other words, capital F is an antiderivative of little f. That's what part A says, in the case where little f is always continuous over the entire interval. Hey, okay. How do you relate that to G? Go back to chapter 4. Both capital F and G are antiderivatives of the same function. We know from chapter 4, as a consequence of the mean value theorem, that means they differ by a constant on the interval. They are antiderivatives of the same function on the same interval. Therefore, they differ by a constant on that interval. Remember that? Therefore, essentially by the mean value theorem, though it's a more direct application of the constant function theorem. I'll go ahead and say by the constant function theorem, the theorem that says if your derivative is always 0 over an interval, then the function is constant over that interval. Capital F of x equals capital G of x plus c for some constant c and for all x. I should say there exists a c in R such that this is true for all x in the interval. And that's the connection between capital F and G that we need. This means capital G of B minus capital G of A can be related to capital F of B and capital F of A. Maybe I should have written this around with capital G there and capital F there. That would have been okay. I'll leave it like this though. Therefore, capital G of B minus capital G of A equals capital F of B minus C minus capital F of A minus C. And that can be related to the integral by the definition of what capital F is. This is the integral of little f from A to B. The c's cancel here, minus the integral of little f from A to A. That's 0. Therefore, we get the integral of little f from A to B. And that does it. So once again, it's a bit tricky. Takes some creativity, but at the same time, it kind of is the only thing you can do. You want to prove this statement here. Assuming capital G is an antiderivative of little f, show that that equation is true. You got to use part A. I guess we'd have to create a function capital F and say, by this formula, and say capital F is an antiderivative. And with enough thought, this is kind of the only thing you can imagine doing. And fortunately, it pops out. Question?
Would theorem statements from like chapter 4 be on the test possibly? Like
Not the exam 3 test, but in the final possibly.
Okay. Perfect, thanks.
But you should still know things from chapter 4 to help you do things in chapter 5. And I might give you a proof on exam 3, like this perhaps, where I'd say you've got to use the constant function theorem, or the fact that antiderivatives of the same function on the same interval differ by a constant. When I say differ by a constant, by the way, that means, you know, if you subtract g of x from both sides here, you get f of x minus g of x equals c. That's what it means to differ by a constant, but you can write that like this too. Let's go ahead and look at a few other problems. Like number 11, that I didn't have a solution for initially. I said I'd go over it today, but the solution is there now. Okay, I updated the file. Actually, number 11 is pretty quick to prove if you allow yourself to use number 10. So number 10 is the more important issue. Let's go ahead and do it that way. Let's look at number 11 first. We'll use number 10 to give a pretty quick proof of number 11. And then we'll spend time thinking about number 10. So number 11 says, suppose little f and little g are continuous on some closed interval from A to B, and that their integrals are the same. The conclusion you want to prove is then there exists a c in the interval from A to B such that f of c equals g of c. Number 10 says, part A at least, number 10 part A, says that if you got a function that's continuous and its integral is 0, then there must be some c where f of c equals 0. Say that again. If f is continuous and its integral is 0, then the function itself has to be 0 somewhere. Should make sense. If the integral is 0, the function could either be horizontal line at 0, or it could be the constant function at 0, or it would have to be partially above the axis and partially below. If you think about the intermediate value theorem, it's got to cross somewhere. That fact can be used to prove this with a little trick. Let H be defined by the difference, f of x minus g of x. Why am I doing that? Trying to use number 10 that says if the integral equals 0, then the function must be 0 somewhere. I'm assuming these two integrals are the same, which would mean the difference of one with the other would be 0.
Do you have to define a new function, or can you just use kind of the backwards of what we were, or one of the properties that we already defined this morning, and say that the integral from a to b of f minus integral of a to b of g is equal to 0, and then kind of use that property backwards to say the integral of a to b is f minus g, and we know that those are equal, so then therefore that would be the integral of a to b to 0, which would then be.
I lost you there, but I think you're on the same track as me.
Yeah, I think
I'm
you're
just being
defining-
sort of more
you're defining
official.
Another function there.
Okay, I lost you there in those words. Okay.
I know I'm smart.
Which I know happens, you know, for verse 2, I know I talk too fast sometimes, too. So I try to say it more than once sometimes. What's the integral of h? H is f minus g. And yeah, by a linearity property, one of the properties we talked about, which is what I think you were thinking of, the integral of f minus the equals the integral of f minus the integral of g. But by assumption, that must be 0. So the integral of h is 0, therefore by number 10a, there must be a c where h of c is 0, and therefore that c is the same c where f of c equals g of c. A implies there exists a c from a to b such that h of c is 0, implying f of c minus g of c equals 0, implying f of c equals g of c. Done, praise the Lord. So if we can use 10a, then it's fairly easy, though slightly tricky. But you start to get used to these tricks, is the idea with these tricks. They are educated tricks. They do come about by thinking about natural things to do, or to try. So the more important issue is, what about 10a? A says, suppose you've got one function, its integral is 0, show there exists a c in the interval so that f of c is 0. The quickest proof of this actually uses the fundamental theorem of calculus. Part A. Define capital F, which domain is the integral from a to b, by the equation capital F of x is the integral from a to x of little f. By the fundamental theorem of calculus, capital F prime equals little f over the entire interval, because little f is continuous over the entire interval. We're assuming the integral of little f from a to b is 0. That means capital F of B must be 0. Also note that capital F of A is 0 because you'd be integrating little f from A to A. And capital F prime of x equals little f of x for all x in the interval. This doesn't finish it. I need something else. My goal is to show there's some c, so little f of c is 0. What other thing do you think I need to get to that final conclusion? This is all preamble. Rolle's theorem, or the mean value theorem, you could say. Applied to capital F. Rolle's theorem, which is really a special case of the mean value theorem, so you could also call it the mean value theorem. It implies there exists a c in the open interval, actually, from A to B, such that capital F prime of c is 0. But capital F prime, by the fundamental theorem of calculus, is little f. Yeah. Part B, I guess I technically assigned but didn't give you a key for as well, 10b. The key is there now. Part B says if little f is continuous and non-negative over the interval. Non-negative means greater than or equal to 0. Then the fact that the integral is 0 implies the function itself must be always 0. If you're assuming it's non-negative, and you're assuming it's continuous over the interval, and this integral is 0, then in fact the function must be the constant function, always equal to 0. That proof actually requires something from chapter 3. I'm not going to go through the full proof, but let's talk about the idea. You could do it by contradiction. Assume to the contrary that there's some c, call it, where f of c is non-zero. We're already assuming f is non-negative, so then, in fact, f of c must be positive. The graph must be up there. And do you remember from chapter 3 about continuity? You had a problem that was just the situation. Assume you've got a function that's continuous at c and positive at c, and you had to prove, oh, what were the letters? There was a u and a v, and an m, such that the function is above that horizontal line for all x between u and v. This horizontal line is not part of the graph of the function. The graph of the function has to be above this horizontal line. The continuity at c is necessary to prove that. Though you only did have to prove continuity at just one point, whereas here we have continuity over the entire interval. Your contradiction here is going to be because of this, because the function has to be above that horizontal line, that's going to mean the integral can't be 0, it would have to be positive. I hope you believe that. Function has to be above the horizontal line at m, where m is positive, over this interval. The integral over that interval would have to be positive. The integral over the entire interval can't be negative. Can't be negative elsewhere. Ultimately, your contradiction would be that the integral would be positive, not 0. I was trying to say you can't cancel out a positive contribution to the integral from this subinterval by saying there's a negative contribution somewhere else because the function is non-negative. That would be the idea of 10b without going into a ton of details. So you should study that proof too. I think I put the proof table here. Actually, I'm not positive now. Another area of application of this stuff is to differential equations. Some differential equations are easy to solve. There's a differential equation. dy dx equals x cubed minus 4x is the differential equation. Y of 0 is 2. This is what I call a pure antiderivative problem. This kind of problem actually comes up very rarely in differential equations because it's just too easy. It's just an antiderivative. What's an antiderivative of x cubed minus 4x? I'm looking for a function whose derivative is that, and also whose graph goes to the point 0, 2. It would just be the integral. X to the 4th over 4 minus, what would it be, 2x squared when you integrate that, plus c. Choose the c to be 2 in this case to make sure it goes through that point. No problem with finding the solution there. And here's the graphical interpretation of it. This is something called a slope field. These two graphs that you see are both antiderivatives of this function, x cubed minus 4x. The slope field, those hash marks that you see, is created by taking each point in the plane, taking its x-coordinate and plugging that x-coordinate into this expression here to find the slope of the solution curve. dy dx represents the slope of the solution curve at that point. For example, when x is 1, there's 1 down there, you can see the slope field has negative slopes along that vertical line. When you plug in x equals 1 into here, you get negative 3, 1 minus 4. Along the vertical line at x equals 1, all these little marks have slope of negative 3. And solution curves have to have a slope of negative 3. That's what the differential equation is saying. Find a function at every point whose derivative, whose slope at that value of x equals this thing. That's why the graphs of solutions have to follow this slope field. And to also satisfy this initial condition, y of 0 is 2, you pick the constant of integration to be 2, and you can see it's the red graph that goes to the point x equals 0, y equals 2. But some functions, like this example, can't be solved in an ordinary kind of way. If you try to integrate sine of x squared in an ordinary kind of way, you will not be successful. It has no elementary antiderivative. It does have a named antiderivative involving FresnelS. Not Kinney of x, sorry. Fresnel got to this function first. Somebody named Fresnel. Maybe 150 years ago, 200 years ago, I'm not quite sure. Got to this function first. Evidently, it's useful enough, we give it a name. FresnelS, why the S? Was that Fresnel's middle initial or something? No. FresnelS because it's related to the sine function. There's a FresnelC as well related to the cosine function. FresnelC. But it is an honest-to-goodness antiderivative of sine of x squared. And if I choose my integration constant to make this happen, I believe FresnelS of 0 is 0, so this would be really this thing plus 2 should be the unique solution of this integrability problem. And you can even have mathematically do it with an integral, though it doesn't plot super fast. It takes a few seconds to plot. That integral plus 2 would be the unique solution of the initial value problem by the fundamental theorem of calculus here. This is an application of the fundamental theorem of calculus, part A. the 2 doesn't affect the derivative, right? The derivative of 2 is 0. I'm creating a function with an integral, where the variable's in the upper limit of the integral. It is an antiderivative of sine of x squared. And it does follow the slope field for that function. So this red graph is the graph of this function plus 2. Kind of a cool looking graph. I'm not an expert, but I've heard Fresnel functions are useful for optics in physics. That's what I've heard. Do you know about it? Have you seen Fresnel functions before?
Yep.
Okay.
Those are math methods.
Okay, there we go in math methods too. All right? From the mouth of the expert about it. Fresnel functions are useful in optics. Why did I have this here? We're going to finish class today by verifying that strange fact. Did you know that? Did you know that's true? Isn't that obvious? Lol. Actually, when my son started saying lol to me sometimes, and then I'm like, what's lol? And he's like, it's LOL. I'm like, well, what is that, lots of love? And he went lol again.
Lots of laughter.
Lots of laughter?
Lots of laughter.
You're better. That's all video.
Usually when you use substitution, it's supposed to help you do an integral. And actually, in this case, it would help you do the integral on the left because the integral on the right, I look at that integral on the right and say that's more doable than the integral on the left looks like it is. Though to do the integral on the right, I would have to use integration by parts 3 times. The z cubed. It wouldn't be too bad. I think I could do it in a couple minutes. I may want to practice that. But, you know, the equality between these integrals means you could do this integral then by doing this integral. But yeah, it's not obvious that these are equal. How would you prove they're equal? It's a substitution related, essentially. Start with the integral on the left. What should you substitute? Well, what should I call my new variable? Maybe z?
Sure.
You might hope z equals natural log of w would be the thing to do. I mean, it seems like the only thing to try. To get in z cubed involved, at least. And then you might wonder, where does the z come from? dz is going to be 1 over w dw. You can also say that w is e to the z. There's an e to the z. And that also means dw is w dz. It's also e to the z dz. So a bunch of running around with different equations here. But this does all work. What happens now when you do the substitution? Replace natural log of w with z. I do get a z cubed. Replace dw with e to the z dz. There we go. The integrand is right now. What about the limits of integration? You do need to change them. W goes from 1 to e. Use this equation to figure out what z does. When w is 1, z is natural log of 1, which is 0. And when w is e, z is natural log of e, which is 1. There you go. These two integrals are the same in value. Now if you actually had to do this one, do it by parts 3 times. Or use Mathematica, or use a table. So sometimes substitution does lead you to an integral that's easier to do, but it doesn't look much easier to do, necessarily. Wanted to do a little bit from section 5.4, but I think we've gone long enough today. Have a good day.